about line graphs. Line graphs are used to show a change over time. They show how two continuous variables are related. So let's look at an example. In this graph, I have two continuous variables, things that keep happening over a time. So we have the weight of a dog, and I have the age of the dog listed on the horizontal axis, and the vertical axis shows the pounds, or the weight of the dog. So both of these are going to continue on. The dog may not continue to gain weight at some point, but you'll be able to continuously measure his weight. So both of these are continuous variables, and the line is going to show how his weight changes over time. When we talk about a line graph, it's important to get the variables on the correct axis. On the x-axis, or known as the horizontal axis, the one that goes this way, is usually the time. So this can be measured in months or days or years or seconds, any kind of time. Ages are also an example of time. The vertical axis, or the y-axis, shows what is being measured. So it might be pounds or temperature or inches or feet or anything that you're going to measure over time. One thing to remember, the difference between the y-axis and the x-axis, it's helpful to me to think about in the letter Y, the part of the Y is tall, it goes up and down, and that reminds me that it's the vertical axis. Let's discuss all of the things that every line graph needs. Before we do that, though, let's look at the graph that we're going to model that with. This is a plant growth graph, and we can see that we have planted a plant and started measuring its height in inches at day 4, and then we recorded its height every day for 1, 2, 3, 4, 5 days. So every line graph needs a title that helps your reader know what it is that they're looking at. The vertical axis needs to have a label, so height in inches, or another graph might have degrees Fahrenheit, or pounds, or whatever you're measuring. Make sure you have a label. The horizontal axis needs a label, and that's usually, again, amount of time, days, years, months. The both axes need to have an equal increments. So we want to have each of our jumps be the same amount. The axes don't have to match each other, but we don't want to jump 5 and then jump 20 inches and then jump 5 inches and then jump 1 inch. We want to be sure that here we've been counting by equal jumps of 5 inches, and down here we're jumping by equal increments, or just 1 day. We want one extra increment on the y-axis beyond the highest data point. So my highest data point on day 9 is around 30 inches. We want to go 1 increment past that always, and so we've marked here the 35 is 1 increment past the highest piece of data that we have. And finally, we want a line that helps us to visualize the change over time. Because we see that this line is generally going up, we can know that the plant is growing in height. When we read a line graph, it's important to know what the line is telling us. We can get quick information from noticing the direction that the line is going. This graph is showing the temperatures on a particular day, and you can see that the temperature was measured every 3 hours and recorded in degrees Fahrenheit. Before we start talking about what the line tells us, one quick thing I want you to notice. Right here we have this little squiggly line, and that's shown on graphs when there is part of the scale that's taken out. If we started our temperature scale at 0, we'd have a huge chunk of space here where we wouldn't have any data. So we use this little squiggly line to say, I've skipped some spaces, some numbers, and then I'm going to start counting at 60. So when we read a line graph, we can know that we have an increase in whatever it is that we're measuring if we see that the line goes up as you read from left to right. So here we can see that there's an increase because the line is slanted up as it continues. There's also an increase here. So we have two groups of 3 hours where the temperature has increased. A decrease is shown on a line graph if the line trends downward as you read left to right. So here between 2 and 5 p.m. and then again between 5 and 8 p.m. the temperature decreased or went down. It's going down as we're reading left to right. If there's no change, that is shown on a line graph by a horizontal line. And you can see here that that's what happened right here between 5 a.m. and 8 a.m. The temperature didn't change, it didn't go up or down, so you just had a data point that was exactly across from the first data point. It's also important to note that the steeper the line, the bigger the change. So if you think about this like maybe walking up a hill, this would be a hill that's not very steep, and so it would be a small increase or a small change. But if you had to walk up a hill that had this kind of incline, that would be a really big, a big increase, a big change, or a big hill. So looking at this graph, we can see here if we compare these two increases, this increase to this increase, this part of the line is much steeper than this one. So the temperature jumped or had a big increase right here between 8 and 11, a bigger increase than it did between 11 and 2. Let's look at a couple of example questions that are the kinds of questions that you might have to answer when analyzing a line graph. This is a graph that is showing Adley's height over, and it's changing over time in years. So we started measuring her height at age 1 and then every year up until age 5. Again, you can see that some part of the scale has been left out here because at 1 she was right under 50 centimeters, so no need to show all of the centimeter measurements between 0 and 50, so we're left down a little bit there. So number 1, between which 2 years did Adley grow the most? Well, if I'm here grow the most, I want to think, oh, the biggest change, the biggest increase will be the part of the line where it's the steepest. And it's easy to see that this part of the line here is very steep compared to each of these others. So between ages 1 and 2 is where she had her biggest growth. All right. Number 2, between which 2 years did Adley grow about 5 centimeters? I think one of the easiest ways to solve this is to label each of the data points and then go back and think about the change that happened between each of those points. So we're going to estimate this was maybe around 48. It's a little bit less than 50. This is close to between 70 and 80, so maybe that's 75. This looks to be right around 80. At 4 years, maybe 91 or so. And the last point here at age 5 looks to be about 96, 95, somewhere in there. So now I'm going back to my question. I want to know between which 2 years did Adley grow about 5 centimeters? Well, here this is obviously way too big, a lot more than 5 centimeter growth. But from 75 to 80, that's about a 5 centimeter growth, or is a 5 centimeter growth. So between ages 2 and 3, she grew about 5 centimeters. Here we have a growth of about 10 or 11 centimeters, which is too big. But between ages 4 and 5, we have another place where she has grown about 5 centimeters. So I'm going to list between ages 4 and 5. And notice that makes sense, that the steepness of these two lines match, which shows that she grew about the same amount in each of those year increments or year jumps. And finally, I need to predict Adley's height at age 6. This is a common kind of question that you'll see when reading a line graph. So notice that I've had about I had a big jump here, which hasn't happened again since then. So in the last 3 years, she's grown 5 centimeters, about 10 centimeters, and about 5 centimeters. So I want to think of an increase that's somewhere between 5 and 10 centimeters. So if I take 96 and add, let's say 5, then somewhere around 100, 105 would be a good prediction. So I'm going to say that I think she's going to be between 100 and 105 centimeters at age 6. And that would show up about here on the line graph, which would be an increase that would make sense.